session, and therefore it is important to start on time because some people have train to catch. Right. And the first speaker is Jack Barton, who is going to speak about linearity of finitely generated presented groups and its connection to the existence of good geometric action. There is Candy here.
Yes, thank you very much. We have a handout. Some of you might recognize the handout. Okay, so G is a group. What sort of group? Well, let's just start with G being a hyperbolic group, a word hyperbolic group. And we have the amazing results of Agel and...
Do you have copyright permission?
Probably not, no. Is it a small enough percentage of the book that it... So, yeah, Agel and Wise. What are they saying? Well, we can certainly interpret it as, for hyperbolic groups anyway, good geometric action implies nice group theoretic properties. So if G is acting geometrically so properly and co-compactly on a cat0 cube complex, then we get these amazing consequences, and in particular from the point of view of the group theory, and especially linearity, which is what this talk's really about, it virtually embeds in a right-angled arting group, finite index subgroup of G with H a subgroup of a rag. And one very strong consequence of that, although there are plenty of others, is that H, and thus G, because this is a commensurability invariant, is linear, and not just any type of linear, but linear over the integers, and that's really, really, really strong. So what happens if we move away from the word hyperbolic world? Things are a lot less clear. And in particular, for the talk, I'm actually going to be considering finitely generated groups. They need not be finitely presented as in the title, but the title was given in before the talk was written. But these groups, if we now say we're not going to suppose that our group is necessarily hyperbolic, I think the classic counterexample for many things, but certainly for this, are the Burger-Moses finitely presented and certainly finitely generated simple groups, abstract simple groups. In particular, they're not linear or at all or residually finite at all, but they have a nice geometric action on as good a space as you could want, really, a product of trees, so two-dimensional cat0. So things look bad, but I'm also going to suggest that it's bad the other way. What about groups that we would regard, or at least I would regard, as nice from a group theoretic point of view, but bad geometrically, so the other way from that example? And I want to propose that the Baumslag-Solitar groups, or at least one Baumslag-Solitar group, is a good candidate there. So the one I'm going to take is the one where you have two generators and your stable letter is conjugating the other generator just to its square. Now, of course, if you're interested only in hyperbolic groups, then all Baumslag-Solitar groups are bad, even Z cross Z. But for non-positive curvature, some of them are okay. Z cross Z is okay. But what about this one? This is bad geometrically, but I suggest it's good group theoretically. So why am I saying that? So as a group, this one is linear. And it's linear in quite a straightforward way. So if that matrix was my element A and that matrix was my element T, looks like it's linear over Z. Of course, this has determinant too, but it's linear. It's linear over the rationals and even the ring Z with half adjoined. It's got, what else could we say about it? It's got cohomological dimension 2. That's quite a nice property. It's coherent, and rags are not in general coherent, so that's when every finitely generated subgroup is finitely presented. And the word problem, well, the actual word problem in this group you can solve very quickly, directly by a variety of means. So if we regard that as group theoretic, then that's good. So now let's go over on the other side to what's going on geometrically. Well, it's got no nice action at all on pretty much anything, has it? I mean, the point is that suppose you have a translation function, a stable or a asymptotic translation function, which goes from your group to the non-negative reals, and all you require, well, suppose you require that it is multiplicative, so stick a power of an element in, and out comes mod n times that translation length. And if you also, and conjugacy invariant, so any function that satisfies that would, if it existed on this group here, have to send a, of course, to 0. And in any reasonably nice space that you're going to be interested in, that's going to imply that a has a fixed point, and it's got infinite order, so you're certainly not going to get a proper action. So that's looking bad. I should have said about the word problem. The geometry of the word problem is nasty because it has an exponential Dane function. So if you try and measure it in that way, it looks bad, but directly it's okay. And of course, one thing that's going on that we'll be looking at later is what's really underlying this fact is that the infinite cyclic group generated by that element A is distorted in the group G. We've certainly heard that mentioned throughout the week. Okay, so things look bad both ways. But what I'm going to try and suggest today is that the right type of linearity should mean a good geometric action. And both the right type of linearity and good geometric action will be defined. Should mean, though, I'm going to leave a little bit vague, but I'm interpreting it here as the implication holds in the groups that we care about. So, okay, what do we think right type of linearity should be? Well, a good guess would be, a sensible guess, a perfectly reasonable guess, would be over the integers, as we've already seen that occurring for hyperbolic groups. That actually turns out that it's not going to be that, but we're going to bear that in mind as a test case, as a working example. But before we go into that in a bit more detail, let's just think of linear groups in general. What is the definition of a linear group, right? It's saying a group is linear if it embeds, if it can be found as a subgroup of the general linear group in some degree, some dimension d, over f, where f is just some field. Any field, in principle, is allowed to occur here. Now, I bet when you think of a linear group, though, you think of your favourite linear group, I suspect most of us are actually thinking of matrices with entries that are complex numbers, or even subrings or subfields of that. And that's actually, most of the time, that's a pretty sensible thing to do, because a nice fact is that if this field f had characteristic 0, so 1 plus 1 plus 1 plus 1 plus 1 and so on is never equal to 0, and the group G is finitely generated, which is our focus in this talk, then you can take, without loss of generality, that field to be the complex numbers. That works because as the group is finitely generated, you take all the entries, the finite number of entries in the generating set, and that's the field that you can work in, and That's basically a field where you can add a certain number of transcendental elements, and then you take a finite extension. And because C has got lots of transcendental elements and is algebraically closed, you will, without loss, you can embed your field into C, so you can pretend that you were in C in the first place. So that's very useful. But it actually turns out that here, today, the right type of linearity, the one that I want to talk about, is where you have a field F where the characteristic of F, usually denoted P, is positive, is strictly positive. So 1 plus 1 plus 1, so on, will eventually equal 0. Now, you might think, well, what fields am I talking about? So obviously, you could take the finite field with P elements, but you're not going to get infinite groups that way because you've only got finitely many possibilities for your entries. So at this point, you might think, take the algebraic closure, and that is an infinite field, but it's locally finite, so the groups you'd get would be locally finite. So if it was finitely generated, you'd again actually only get finite groups. So you absolutely have to come along and add a transcendental, an indeterminate. In fact, generally you have to add several. And you could keep on going as many as you like, or countably many. And then you might want to take the algebraic closure of that. So those are the fields that we're thinking about and going to use. Now, how's the handout going? Has everyone got or is near a copy of the handout? So here's what I want to do now. So okay, so we've got two rival notions for right type of linearity getting us good geometric actions, over the integers or over a field of positive characteristic. So we now turn to page 439 of Brideston Heffliger, and we're going to be interested in actions on cat zero spaces, suitable actions on cat zero spaces. And so we look at the what we already know theorem, so it's summarizing results from earlier on in the book. So here's our first candidate for good geometric action, which is the first part of the theorem. And this is when a group acts properly and co-compactly. And it turns out that that's not going to be the right notion for either of those two types of linearity. So if we sort of do a little comparison with the integers and positive characteristic, let's look at these properties. So you want to replace it by, suppose a finitely generated group gamma is either linear over Z or linear in positive characteristic. Are the following true? So number one, is this group necessarily finitely presented? No, in either case. So F2 is linear in any field. So F2 cross F2 is linear in any field, and that certainly has finitely generated subgroups that are not finitely presented. This thing about finitely many conjugacy classes fails in both cases. The examples I know are direct products, subgroups of direct products of SL 2Z, and that's linear in any in any field because it's virtually 3. Every solvable subgroup of gamma is virtually abelian. That's false as well, actually, in both cases. There is something, though, for linearity over the integers, which is that every soluble subgroup is polycyclic. That's a well-known algebraic fact that can be found. Every abelian subgroup is finitely generated. Well, actually, the integers, linearity over the integers does satisfy that one because soluble implies polycyclic, so if it were abelian, it would be finitely generated. Fails for characteristic, positive characteristic. And the last one is to do with being fundamental group of compact cell complex. So one has already failed. So it's not looking good, is it? This comparison in either of these cases. The integers managed one goal, one tick. The characteristic, positive characteristic, nothing. So let's now go to the next part, which is where we consider and compare G a or it's actually H, a finitely generated group, and we look at the properties that are satisfied if it acts properly by semi-simple isometries on X. So the inf of the displacement function is attained. So what do we get? So let's look at the integers and positive characteristic again. So let's deal with the integers first. In fact, well, let's speed this up. In fact, for the fifth property is only to do with hyperbolic groups anyway, and we're outside that, so that fails automatically. For linearity over the integers, that third one, the one about what I call, or Danny Wise calls, balanced groups, groups that are linear over the integers do have to be balanced. So 3 does hold, but 1, 2, and 4 all fail. And there are easy counterexamples. The Heisenberg group of upper triangular 3x3 matrices, 1's on the diagonal, integers elsewhere, will destroy all of those. So again, it's not looking good. But the theorem today is that if a finitely generated group H is linear in positive characteristic, then 1, 2, 3, and 4 all work, and they go through verbatim. There's no need to have to change any of the statements here. So that's looking good, because these are obstructions. These can be thought of as obstructions to having a nice action properly and semi-simply on cat-zero spaces, and they're also going to be obstructions for being linear in positive characteristic. So we might look at some or all of the proofs. I should just say at this point, I want to acknowledge helpful correspondence with Martin Brighton, in that one thing you do want from your... Okay, so right type of linearity is now defined, and it means finitely generated and linear in positive characteristic. Good geometric action will now be defined. It means proper finitely generated group acting properly and semi-simply, and it's certainly on a space, a cat-zero space, more general than a cube complex, and it's wise to put complete here, and if you do that, that allows these the semi-simple property to be lifted up to finite index supergroups. So you get that it's a commensurability invariant, and you're going to want that if you're going to compare it to this, which is definitely a commensurability invariant. So that's the notion of good geometric action. Okay, so let's at least outline some of these proofs. The one about balanced, which one was it? I think it's number 3. Number 3 follows from even cyclic groups being undistorted. So if you do 4, then you've done 3. So I think we'll do 1 and 2, or outline 1 and 2, and it's going to involve playing around with matrices for a little bit anyway. So, okay, so what are we trying to prove? So what we want for part 1, H is finitely generated and linear in positive characteristic, and we want to be showing that every polycyclic subgroup of H is virtually abelian. So at this stage, it's worth pointing out that I will not use the linear in positive characteristic very much. Most of this will go through for arbitrary groups of matrices over arbitrary fields. There'll just be a couple of places where it will kick in, but it will be in important places. So what do we do? So actually, you can start with the hypothesis that H drop down to the subgroup. We will not assume yet that it's finitely generated. So we're going to assume that H is solvable and linear in positive characteristic, and that field is algebraically closed. So basically, we're going to use Jordan normal form. Well, actually, we're going to use the Lee-Kolchin theorem, or also credited a slightly different version to Malsive, which says that there will exist a finite index subgroup G of your soluble linear subgroup H, any soluble linear subgroup, such that you can make this upper triangular. You can conjugate it simultaneously into upper triangular matrices. So, so you do that. So you do that. Okay, now the point then is when you multiply upper triangular matrices together, the one thing you do know is that the diagonal elements just multiply. So all that's saying, in group theoretic terms, is you've got yourself a homomorphism theta from the group to the multiplicative group of the field, or the direct product of D copies of that. You're just picking out each of these. That is a homomorphism because of that point. And the kernel, of course, is what's sometimes called the upper unitriangular matrices. It'll have to hit the identity in every place here. So there we are. Okay, so far so good, but so what? The point is here that this is an example of a unipotent matrix. So that's one where, in the algebraic closure anyway, all eigenvalues are equal to 1. And here's the key fact about positive characteristic, which is clearly not true in normal matrices, usual matrices over the complex numbers, is that unipotent implies finite order. That is the crucial fact that we use here. So in particular, this, when we're in positive characteristic, if you're trying to play with the Baumslag-Solitar groups, that, or whatever entry you put there from the field, it will have finite order. Well, yeah, and you can see that using the Jordan decomposition, or you can do it directly using the binomial theorem, or so on. Okay, so where are we? So we've got ourselves okay, we've got the fact that the kernel K is therefore, in the positive characteristic case, a soluble torsion group, solvable torsion group. Now we know all about torsion groups, and they need not be finite in general. But now suppose we move to G being polycyclic, which was actually the original hypothesis, or H is polycyclic and we're taking finite index subgroups, so we're still polycyclic. Then every subgroup is finitely generated. So K is now a finitely generated solvable torsion group. So K will be finite. And so that gives us that the quotient G over K is abelian, because that was the whole point of taking K. We're going on to an abelian group here. So G is finite by abelian. That's not enough to show virtually abelian if G is not finitely generated, but if G is finitely generated, then you've got that G and hence H is virtually abelian. So that's the first property proved. So yeah, here's a really silly application, certainly known, but it illustrates the point. So for a really silly example, let's take SLNZ. This has certainly been playing a role this week. So we want to know, when is it linear in a positive characteristic? Well, of course, you might say, look, it's not. It's linear in characteristic 0. But I mean, when is the abstract group linear in positive characteristic? And the answer is yes for n equals 2. And by, for instance, this result, it's no for n at least 3. So that's sort of, you can see where that's fitting in with this claim. Right, the next one is about centralizers, isn't it? So turning to the handout again, part 2 of the second part, every finitely generated abelian, the quasi-isometric one I want to leave till the end, so I'm actually doing number 4. If you've got an abelian, free abelian group of finite rank A, which is central in your group, there's a subgroup of finite index that contains A as a direct factor. We'll have a look at that, or a slightly simplified version of that, at least for now. So again, it's just going to be mucking around with matrices and using the diagonal entries of upper triangular matrices. So what do we do now? Okay. So we'll just do it for rank 1. The general proof for rank n is pretty similar. So what am I doing? I'm taking H to be actually at the moment H will not need to be finitely generated, but H is certainly linear in positive characteristic, and I am given an element A which is central in H. It commutes with everything in H, and it has infinite order. And so what do we want to do? We want to look at the we want to look at what we can say in that case. So the conclusion here for us will be that the natural abelianization map, so given any group, you can send it to its universal abelian quotient just by cutting out the commutator subgroup. That is always injective on the element A. A will have infinite order in the image. So how do you do this? Well, put A in a nice form, Jordan normal form, say. So you have eigenspaces and generalized eigenspaces for each, probably not going to be big enough, for each eigenvalue, each distinct eigenvalue. We're working over the algebraic closure, say, and then turn it into upper triangular matrices in each block. That's basically all you need, but Jordan normal form will certainly do that. So this is meant to be lambda 1 down the diagonal, zeros below, and whatever here, up to the kth eigenvalue. So we get a corresponding generalized eigenspace, a block there. Now the point is that if you work out what properties a matrix has to have that commutes with A, it has to send, we know it sends eigenspaces of A to itself, and not any eigenspace of A to itself. That argument also works straightforwardly for generalized eigenspaces. So what that is saying, because H commutes with A, so this is for any little h in big H, it just splits into blocks of the same, the corresponding size and position as we got for A. Now we don't know that it's upper triangular in each block. Actually you can simultaneously upper triangularize A and H, but you're not going to be able to do that in general over all elements H in the group. So just assume it's just blocks of any old stuff here. So now the equivalent of our picking out the diagonal elements homomorphism to get us into a abelian group here, which has to be defined on the whole of H for this to work, is going to be you use the determinant. That's a very good homomorphism from matrices to an abelian group, but you do it in the blocks. So this is a well-defined homomorphism. You're just taking the dead of that, the dead of that, the dead of that, the dead of that, and so on. So maybe let's write that. So where delta of H is det of H1 and so on, det of the kth block. So we can see exactly what happens to A. It just goes to powers of these eigenvalues. So delta of A is sent to lambda 1 to the, if that was dimension D1, all the way up to lambda k to dimension dk. Now you suppose, suppose this had finite order. What would happen? Well, then each of these eigenvalues, you'd get a power which is sending you to 1. So the eigenvalues are all roots of unity. So by taking a bigger power of A, you can find a power. Yeah, you get a power of A which is unipotent again, that hasn't used the positive characteristic really, but at this stage we can now say that that implies that A would be a finite order. There's your contradiction. So A has survived as an infinite order element on applying some homomorphism from the group to an abelian group, so it certainly survives in the abelianization because that's the universal abelian quotient. Okay, so then just to finish it off, at least in the case where n equals 1, we actually wanted it to split in a finite index subgroup. So what you do there is, if the H, your original group here, is finitely generated, then when you apply this, the universal abelianization map into, you can then, because we know about finitely generated abelian groups, you can then go into a copy of Z in which A embeds as an infinite order element. So it's got finite index subgroup in that. You then pull back, so you get your finite index subgroup going on here, and basically that is the kernel of the map times times your element A. So there it is splitting as a direct product, at least in a finite index subgroup. So here's a straightforward corollary of that result. I mean, basically, if these obstructions have been applied to groups to show they don't admit nice actions on cat zero spaces, then whatever groups that happened for, we can just do it straight away to say it's got no positive characteristic linear representations. So in immediate, following a result of Bryson, it follows that the mapping class group of a closed orientable surface, in fact, will take the genus to be equal to be at least 3, although it can have any number of punctures or even boundary components. That is not linear in any field of positive characteristic. And that's done, well, you just use the result that's sitting there, which is that when you take a Dane twist, any Dane twist around any simple closed curve, the centralizer in the mapping class group of the Dane twist, centralizer of that Dane twist in the mapping class group has finite order abelianization. Nothing survives as an infinite order element. You do that by seeing the centralizer by cutting along the curve and describing the centralizer in that way. So essentially you're reducing it to another mapping class group, and you know what the abelianizations of those are. But if you go too low, if you're in genus 2 and you chop it, then you're now looking at the abelianization of the mapping class group in genus 1, so that doesn't hold. I should actually say that for G equals 2, the mapping class group is known to be linear over C. That follows from the braid group linearity results. But having said that, a warning is I'm not sure this result gives us a lot of indication either way as to whether the mapping class group in higher genus is actually linear or not. I would just say that if you want to show it's not linear, you only have to do it over the complex numbers. Best of luck with that. If you want to show that it is linear, similarly, just restrict to the complex numbers, but you've got to make sure that every Dane twist in your supposed representation that's going to be faithful is mapped to unipotent elements, because otherwise the proof will break down as here. So yeah, okay, so let's moving on. So now we're actually going to, those two results were really just playing around with matrices. So now we're bringing in part 2 of the second property on the handout. Every finitely generated abelian subgroup of H is quasi-isometrically embedded. I'm going to use undistorted, and of course it's with the choice of any word metric. So we'll first look at the case, so this is distortion or undistortion really. We're first going to look at the case where your abelian group is just infinite cyclic. So the hypothesis is you've got an infinite cyclic group inside a finitely generated group G, which is linear over some field of positive characteristic. Now, right, so I came up with this argument, which I thought was really neat before seeing all those properties, and then I thought, right, okay, so that's cyclic done, let's move to a bin. It actually turns out that basically the exact argument was for cyclic groups was known already. It's in a paper of Lubotsky, Moses, and Raghunathan from 2000, a very detailed and deep paper, but they follow exactly this route that we're now going to describe. So how do we get cyclic subgroups to be undistorted? Here's probably a very well-known and natural way of doing it. What you're after is a function from the group G, the big group, the finitely generated big group, to the strictly positive reals, and you guys just require two properties. You want the f is what I call submultiplicative, so f of a product is less than f of g times f of h, and then the second thing is that there exists a real number k bigger than 1, but maybe only just bigger than 1, so think of it as 1 plus epsilon, so the function is defined on the whole group, so you can apply it to A, but you can apply it to any power of A, and if that power, if you get you want an inequality from below as well, so suppose that holds, then it's an easier, I mean it's just, well the point is that you'll get an upper bound here, you'll get that holds for k to the word length of a to the n in the big group G, just by taking the maximum over the generators of G and their inverses, because this group is finitely generated. You just take logs, rearrange, and you're done. But we need a function for this to make this happen, and there's one very natural one when you think about it. So these elements, G, are not just abstract group elements, they are matrices, they are linear maps, they are linear operators. So you use the operator norm. So just to remind you briefly, the operator norm on a matrix, I'll write it with the norm and the op there, is you look at what it's doing to every non-zero vector and its length there, and then the length of the original vector, you take the sup, we'd better not divide by 0, but otherwise any v is allowed, and let's put, say, the max norm, the sup norm on the vector space itself. So this is submultiplicative. That's a very useful and well-known result. Moreover, suppose you have an eigenvalue and an eigenvector, then what you'll get is that the operator norm has to be at least as big as the modulus of that eigenvalue, because we know that mv is mod of lambda, norm of lambda v, which is mod of lambda mod of v over v. So you'll get that. And so you're done if this matrix, i.e. you've got the properties you need, if this matrix has an eigenvalue of modulus bigger than 1, and if modulus of less than 1, you can just replace A by A inverse. So we're done. Or are we? Well, it looks like we're done, but there's a couple of things that have been skipped over slightly here. And so the first one is I was kind of blurring the distinction between a root of unity, so that's an algebraic thing, a finite order element in the multiplicative group of the field, and having modulus 1, which is actually analytic, saying it lies on the unit circle. They're not the same thing. And then the second thing is, what does modulus even mean anyway when we're over a field of positive characteristic? That was really being done, or can be thought of being done overseas. So, so yeah, let's have a think about this. What is modulus for f characteristic bigger than 0? Well, anyone who's done a bit of number theory might know about local fields, global fields, and so on, and we're really talking here about absolute values, or closely related notion of valuations. So what you're doing, what you want is a function which I'll write nu, which is the modulus, is the abstract version of the modulus of a complex number. So what properties will we want? We'll want a 0 property. It returns 0 if and only if you have the 0 element. We'll want multiplicative. We want it to be actually multiplicative. And we'll want, mod of x, y is mod x, mod y. And we'll want additivity. And that's it. So anything satisfying that on any field can be called an absolute value. And the point is, you don't have to stick to the modulus in the complex numbers that you know and love. In fact, you have to go away from that. And so what these guys realized, and I did exactly the same thing, is you go to the, how did Tietz prove the Tietz alternative? What about orthogonal matrices which have infinite order, but every eigenvalue has modulus 1? How are you going to play ping pong with that? You know, people say, oh yeah, the Tietz paper about free subgroups in linear groups, it's ping pong, but you've got to set it up so that it is ping pong. In that situation, you know, 2 rotations of infinite order through the origin can generate a free group, infinite order, but there's no ping pong there for that action. So you've got to replace your absolute value by a suitable alternative. And what Tietz says is that if f is a finitely generated field, then there exists an absolute value in this sense on any field of any characteristic with its modulus not equal to 1. Okay, provided lambda is not a root of unity. So what we've shown here, what this argument is doing, is saying that if you can't get this inequality to work, then you've actually got a unipotent or a virtually unipotent matrix. And in characteristic 0, that of course could happen, but in positive characteristic, that's going to mean you have finite order. And so if A is an element represented by a matrix of infinite order, then that's not going to happen. Right, so that's the cyclic case. So I've been working on the abelian case, and having found that argument in the literature, I thought, right, okay, I need to push this a bit, push this forward, see if we can actually do the abelian case. And at first, I thought that this wasn't going to work in general, these sets of ideas. So the general setup now is you've got an abelian subgroup, let's say free abelian, because you can drop down to finite index subgroups, and that preserves distortion or undistortion. So it's isomorphic to the free abelian group of rank M, sitting inside GL of df. Now, for the moment, f is any field. In fact, for the moment, actually, f is going to be the rational numbers, characteristic 0. So the problem is, or what I thought the problem would be, is that you can certainly have rank bigger than your dimension. So you're somehow squashing the group up into a much smaller linear group. And the obvious example, or an obvious example, is just look at the group in the rationals, generated by 2 and 3. That's a z cross z, right, multiplicatively. And you're going to be in trouble if you try and get the word length bounded below, the mod r plus mod s bounded below, if you're just using the usual modulus, because, you know, if you take logs, the additive group generated by log 2 and log 3 is dense in the real, so that's not going to work at all. Now, the point is that first of all we saw that we didn't have to use the standard modulus. We could use other absolute values, valuations, and of course over the rationals we've got the p-adic ones for p prime and similar over number fields. But we don't have to use the same one. We can use different ones. So this is how you get out of this. If that element is A, then the function, or a similar function to this that will work, is you take the 2-adic valuation of this, which is just picking up the r. It's say a half to the r, or however you want to normalize it. So, and you log that and you modulus that. So that's the usual modulus in the real numbers. And then, yeah, because log maps to negative numbers. And then you do the same for that. And rather conveniently, that will pick out the r and the s separately. And so it's bounded below by mod r plus mod s, which is the word length in A which you're after, times whichever one is smaller out of log 2 and log 3. So k is log 2 there. So so that's what saves us. So in fact, we can prove this for general rank M abelian subgroups in finitely generated groups over positive characteristic. I'll just give a little outline of how that goes. You do have, I would argue, you do have to work a bit harder here, but the same techniques are getting you there. So what you do, okay, so I've just rubbed off that f function which had to be submultiplicative and have that lower bound. So you actually want, for each I between 1 and m, so for each element of the free generating set of your abelian group, what you'll be after is a function fi, so from the group, from G, the big group, to the positive reals again, and you'll want that to be submultiplicative as before, and you'll also want it to satisfy the property. Okay, so I've got to write out a general element of A as something like A1M1, A to the M, NM, but that's just a general element of my free abelian group A. And if that can pick out the ith index here, so there's some number, real number strictly bigger than 1 ki, such that I get that, then I get my bound the other way because it's submultiplicative by looking at the generating set, multiply it all together, take logs, and that will give you undistorted abelian groups. So how are we going to find these FIs? So a quick summary here is basically using this idea in various contexts. So what you do, what you're going to do is you're going to suppose that you look at the right. So what I haven't said right at the beginning is that without loss of generality, once we've got our free abelian group A, which is linear, we're going to make A again upper by conjugation, simultaneous conjugation. We're going to make A a load of upper triangular matrices, and in particular the generating entries, the generating matrices here are upper triangular, so we can read off the diagonals and so on. Now, suppose you have, it's going to look a little bit odd, but suppose you have for each I, for each generator, you have an absolute value, and you also have some diagonal element depending on that I. So this j is a function of I, but where, okay, so if you apply, I've got no idea how to write this out in a sensible notation, but here we go. So you take any one of these generators, say the kth generator, that's a matrix, that's an upper triangular matrix, and you're only really interested in its diagonal entries, and you hope that there is a diagonal entry such that when you apply the absolute value, you get 1 if you're not at the particular AI that you're interested in, and you get not equal to 1 if you hit the one that you are interested in. So it's just like the 2-adic and the 3-adic. It's picking out the bits. It's picking out the individual bits. So if you have that, then basically the function that you'll consider will be, the individual function will be the operator norm. Actually, this is defined on the whole of G. The operator norm using, so you've got a field, so you're first putting an absolute value on it, so you've got a modulus, then you're putting the sup norm on the vector space, which is d copies of that, and then you're putting the operator norm on the matrices. If you do that, by the fact that the operator norm is bigger, or at least as big as any eigenvalue, and hence any diagonal element, then suppose that were mu I, that number there. Oh, and without loss of generality, you're going to turn it bigger than 1 because you'll just replace the generator by its inverse if it were less than 1, so the diagonal entries become 1 over the diagonal entries. And then you have satisfied the properties that you require, and you're done. Right, we're nearly done, but with this rather so this shows that we can get such functions with the property that will give us non-distortion of A, provided we have valuations that somehow pick up exactly the right piece. But that seems rather convenient. You know, in this one, hang on, the 2-adic evaluation will pick up that, and the 3-adic will pick up that. Very nice. But, you know, this is a general finitely generated abelian group that we're given. But in fact, it's nothing other now, essentially, than a change of basis. So what you do is you take lots and lots of valuations, a finite number, but you can show that if you take R, now here's the only other place I think where I'm using positive characteristic, is that the valuations will be discrete valuations. What that says is when you take logs, you can assume that the image is actually the integers. It's just the various powers of a particular number. So your map is actually getting you directly into the integers and not some sort of mixed up copy as the problem is over there. And you can take enough such that your abelian group will embed in a big free abelian group. And basically, if you took n of these, you just apply them to all of the diagonal entries, which is a homomorphism because these matrices are upper triangular, so you're just picking out a diagonal entry and then and picking it up over the various valuations. So now you've embedded A here. It's just essentially a change of basis. It's sort of like reducing a matrix to echelon form. Now you're sort of doing it over the rationals because you might have to divide by a positive number, but you can always drop to a finite index subgroup. So actually you will be able to get this, and so we do have that finitely generated abelian subgroups of finitely generated groups over positive characteristic are undistorted. So in the last few minutes I just want to point out some related results, observations, and so on. So while I was preparing this talk, a paper appeared on the archive in early December by someone who I'd never heard of before, but he's got a wonderful name, I think, Derek Wigglesworth. And he showed that the same thing holds, that we have non-distortion of abelian groups for the outer automorphism group of Fn. And that's a nice complementary result because, in fact, for n at least 4, that's known not to be linear at all, not over any field, not in characteristic 0 either. I think n equals 3, it's still open. And what's interesting is looking at this paper, I think he's a student of Besvina, and it's a case of you have to master all the technical results of your supervisor and work hard to get this up. But you can see the overview is almost identical to this overview, that you're picking out, you're finding certain functions that pick out the powers, and you're doing that by finding maps to Z. So that's interesting. So yeah, we'll just finish up quoting some results. So where I came in, okay, so I'm interested in the question, are all free bicyclic groups linear? So if they're hyperbolic, because they were cubulated by Mark Hagen and Danny Wise, they're even linear over Z. But what about the so let's express this, are all non-hyperbolic free bicyclic groups linear? And of course we have a test case that's already been mentioned by Daniel Woodhouse, which is Gersten's group, so I don't need to explain that. So I was playing around trying to show that Gersten's group was linear over the complex numbers in characteristic 0 and coming back to it and still getting nowhere. And eventually it ended up being a proof that in fact Gersten's group is not linear in positive characteristic, which makes sense with the analogy with having a nice action, because it was pointed out that it does not have such an action. So but the linearity in general for Gersten's group and free bicyclic groups still open. Finally, I want to say a word about what groups do we know are linear in positive characteristic, and there's not as many known to me as I would like, I think is the point there. So what have you got? You've got lattices, free groups. You can take direct and free products, that will still preserve linearity. You can, it's commensurable, that was already mentioned, I think. Limit group, basically I think this is Malsive, anything that's fully residually something that's linear in a particular dimension is itself linear in that dimension. So you do get a fair bit. Some free products with amalgamation over abelian subgroups, but you have to do it pretty much case by case. What I don't know of are, so three manifolds groups would be an obvious candidate. And here, if you just go for the 8 geometries, for getting hyperbolic, the other ones are exactly when the manifold has a, let's say just closed 3 manifold, admits a metric of non-positive curvature. So there the analogy is working really nicely. But for closed hyperbolic 3 manifold groups, I don't know of any that have been shown to be linear in positive characteristics. So I think that's an interesting question. And finally, of course, it would be silly if we didn't mention rags. And you really want rags to be linear in positive characteristic because of their nice geometric properties. Now, the problem is that the proof I know that rags are linear, and indeed linear over Z, which gets us all those other groups linear over Z, goes through right-angled Coxeter groups, and the linear representations you get there have loads of unipotent elements in right from the start. So that is not going to work, because they're the ones that become finite order in positive characteristic. So what do we know of rags? Well, there's some basic ones that you're going to get. I do have one result, which is I've also been playing around with that one because I was interested in the minimum dimension that you could get a faithful linear representation over the complex numbers, and this was a good candidate to see if you could do it in 3. And you can embed it in GL3C, but the proof is quite algebraic, so it also works over a field, algebraic closed field of any characteristic. So we at least get those, and we get rags that are commensurable to those. We've been hearing a lot about that this week, and that includes all trees. So we do have some rags, but we really need them all, and that's where I'll stop. Thank you.
We have time only for one short question.
I have one very short. So you mentioned linearity of free products, I think.
Yes.
Over any characteristic? Or?
Yes, I think it's a very old theorem, and I'm not quite going to get the name right, but something like Nisevich. I think we're talking 1940s or 1950s. So it says that if you've got two groups, and I don't think you need finite generation. So if you've got two groups that are linear in over any field of a given characteristic, then the free product is linear, and I don't think you have to go up in dimension. You might have to go up by 1, so let's play safe. And the field might change. It might have to be a bigger an extension field, but it's still of the same characteristic. So that's a very old result, probably the first result.
I suggest that further questions will be in private. So I think we take 3 minutes of break, just enough to clean the blackboard, and then we continue.